let's consider a simple example so we get a better intuition of what conditional expectation means. So it will be the discrete version of conditional expectation. So suppose we break our sample space, omega, we break it into pieces, finitely many pieces. So let's say finite or countable. So here, let's add here finite or countable. Of course, we want this partition to have measurable sets in it. And now we take G to be the sigma algebra generated by C. And well, of course, what is the sigma algebra generated by a partition is just collection of subsets of unions of elements in the partition. So if C is the partition, we look down here, and then what is a typical element in G? G will have the whole set, you have the empty set as usual, it will have every set A which is in C, but it also has unions of sets that are in C. So this set here in blue, we can call this set C. This will also be a set in this sigma algebra G. Okay, so G would be this. It would be just the set of all possible unions of elements in this countable partition. And then in that case, what is, to help us improve our understanding of conditional expectation, what would be the expectation of X given G? This is the notation for conditional expectation that we're calling Z in these in the lecture notes and in these slides. What is the expectation of Z, the condition of expectation of Z given G? It will be nothing but, let's go back down here, it will be nothing but a variable that on each of these elements of the partition is constant. Here Z is constant and equal to the average value of X on this set. Let's call this set AJ. So here's my set AJ. Okay, and what do I mean by average value? Well, the average value is, of course, we compute the expectation of X on that set AJ, and we divide it by the measure of AJ. And then you ask, well, what happens if the measure of AJ equals 0? And then the answer will be, if we're assuming the partition is countable, well, there will be plenty of them that will have positive measure. And if we add the measure of all those that have positive measure, we get 1 in the end. They will add up to 1. So we can completely disconsider the sets that have 0 measure, meaning just define Z to be whatever we want on those sets. It will not have any interfere with the property of Z being indeed a conditional expectation of X given G, because as we have discussed already, changing the value of Z on a set of measure 0 does not break the property of Z being a conditional expectation. So let's resume where we are. We just said if this is 0, it doesn't matter. On those parts of the partition that if they have measure 0, we can define Z to be anything we want on those blocks of the sample space. And if it's non-zero, we can compute this average here. This will be the average of X on that block and just define Z to be continuous on that block. So this is the notion of conditional expectation. And this is to help us improve our intuition and our understanding. And now finally, let us connect the notion of conditional expectation with the tool that we're going to use as an application of Radon-Nikodym derivative, or the Radon-Nikodym theorem, is existence. We have discussed uniqueness. We have discussed if Z equals the conditional expectation of X given is the conditional expectation of X given G. And if we have already discussed that, well, if W is also measurable with respect to G and W equal Z almost surely, then W also equals the expectation of X given G, which means this equal, whenever we say that expectation of X given G equals something, this equal is already to be understood that we don't care about what happens on sets of measure zero. You see this notation here is not present in the lecture notes, because in this module, you're not going to explore so deeply the notion of a conditional expectation and its properties. This would be the sensible notation if we would start exploring all the properties of conditional expectation and how they relate. But what we're focusing on now is on the fact that it exists as an application of Radon-Nikodym theorem. So you'll not see this notation in the lecture notes because we're not really adopting this notation in this module. And we just want to illustrate Radon-Nikodym theorem by having this as an application of it. And the statement of the theorem, it is very simple. It says if X is almost surely finite, well, in fact, it doesn't say what happens if X is not almost surely finite. Maybe still X will have a conditional expectation given the sigma algebra G, but it assumes X is almost surely finite, and it assumes the expectation of X is defined. This one we cannot really waive this assumption, because if the expectation of X is not defined, then we cannot possibly make sense of this requirement. Okay, we ask this to be true for every A in the sigma algebra G. And well, the sigma algebra G, it also includes omega. So we can put omega here instead of A. And well, this, we know what this is. This is the expectation of X. So of course, for this identity to hold, expectation of X has to be defined in the first place. So this we cannot really waive, this condition of being defined. And the theorem says, under this assumption that X is almost surely finite and the expectation of X is defined, then the conditional expectation is defined. It exists. There exists a random variable Z that has those two properties that are needed in order for it to be called the conditional expectation of X given G. So we end this part of the video lecture with the statement of the theorem, and in the next part, we'll go through its proof.